Practice 4-7. Now we get to use some more of these CPCTC relationships. First, name a pair of overlapping congruent triangles in each diagram, and then tell me why we get to say that. Okay, let's see. They've already marked the stuff that they're giving us. So ZW congruent to XY. Got it. And these two are right angles. Ooh, ooh, ooh. When you have right triangles, you get to use HL. And you could also use a thing called LL, which would actually be the same as SAS for right triangles. So let's see here. First, let me list what that triangle, the names of the triangles. So ZWX would be congruent to YXW. And then, why do I know that those are congruent? Well, let me look. I have this and this. This is congruent to the other side, so that's one of the legs of the right triangle. Then I've got this side congruent to itself, which is the other leg of the triangle. So I would accept the answer LL for leg of a right triangle. It's also side, angle, side in a right triangle. Number 2, this triangle from A to B to C would be congruent to D to C to B. Oops, D, C, B. Why is that? Let me look. Since I have these overlapping triangles that share this side, when I zoom in here, I can see that I've got this big angle congruent to the one over here. And I also have this little triangle, this little angle congruent to the other side. So I can say that these are congruent because I have angle, side, angle. Let me trace that a little differently so that you can see it. For this yellow triangle, the things I know are this big angle here, the little angle inside this corner, and this side. So this is actually angle, side, angle is the reason why I can say those two triangles are congruent. Number 3, we have 2 sets of parallel lines. We've got these guys here that are cut by a transversal, and we also have these guys here, again, cut by a transversal. Let's look at each individual scenario first. Let me copy these 2 lines over here, and I'm going to draw one transversal this side here. So now, if I'm looking at these 2, clear this up so you can see the triangles, I'm looking at this intersection here is right here, and this intersection is right here. Hey, look, this corner, that angle, is part of this triangle. Super. And meanwhile, this angle right in here, oops, needed a pen, this angle is a part of the other triangle. So I think they're congruent, because why? Because these are parallel lines cut by a transversal, therefore these angles are congruent. What's the name of those angles, by the way? Yeah, corresponding. So I have established that I have this guy congruent to this guy. Great. So I'm probably not going to be using side, side, side because I already have one set of angles established. I'm going to use the exact same logic for the next set of angles. Watch this. Let me talk about these 2. Well, I've got those 2, and they are cut by a transversal. So this angle in here and this angle in here match up with this guy and this guy. Hey look, parallel lines cut by a transversal. What is the name for this pair of angles? Yeah, corresponding again. Bonding, there we go. Yes, so now what do I have? Look at this again. I've got this set of angles. I've got this set of angles. Where can I go from here to prove that these guys are congruent? Well, you know what? If I have two sets of angles, I've got two options here. I can either have angle, angle, side congruence, or maybe I have angle, side, angle. What'll it be? Well, if I had angle, angle, side, let me draw this triangle apart from the other one. So here's E, G, J. And now down here, I've got F, H, K. F, H, K. They don't really have any sides that are in common. Bummer. Let's see. What else could I do? Well, if I had angle, angle, side, then I'd have to do this angle, and then I'd have to know something about this side, or if I didn't know that side, oops, get rid of that guy, then I would go angle, angle, side. Well, I don't know if I can see that really right off the bat. Let's try the other one. If it's not angle, angle, side, maybe it's angle, side, angle. Well, that means if these are the two angles that I already know about, if I have ASA for my congruence theorem, then that would have to be the side that I know about. Is that the side that I know about? Well, here's the deal. Since we know that we have these two sets of angles that are congruent, then I can actually use some angle addition postulate, segment addition postulates to say that this length would be congruent to this length on here. So we'll use ASA for this, and then because EG is congruent to HF. So that would be the side that I'm talking about. E to G is congruent to HF. So I do have angle, side, angle, and that's all I need. So now number 4. They tell us that LP is congruent to LO, also that this part, PM, is congruent to ON. Well, let's see. I have the overlapping triangles that I can talk about would be from L to N to P compared to L to M to O. So let me draw those. And why would those be congruent? Well, let's see here. If I know, and this is like a really fast proof, but if I know that these are congruent because they're vertical angles, and I know that in this triangle, this guy here is congruent to this guy, that means these angles down here would also be congruent. So I'm trying to prove this. I can use angle here along with this side, but I need one more angle. Well, down here I've got angle, angle, side for this little guy. So now I can talk about this side being congruent to this side, and from there I get, where is it? Oh, adding these two together gives me this angle congruent to this angle. So this side, this entire side will be congruent, and so those sides opposite congruent triangle, congruent angles are congruent. So this would actually be SAS. And I'm speeding through these proofs with a lot of scribbling, so if you need some more help understanding why we get to these reasonings, just let me know. I'd love to explain it some more. So number 5, the overlapping triangles, of course, would be ADF and BEG. Oops, BGE, there we go. And why is that? Why can we say that they're congruent? Well, again, this is going to be a side angle side kind of thing. So if I've got this, right now I've got this little isosceles triangle, so that means I get this guy equal to that guy. That's cool. And also, I've got these angles congruent to each other. But what else? Well, I'm actually going to be able to say that I can add these two together, and that would be congruent to adding these two together. Also, since EF is congruent to itself, I can add the DE to EF and the congruent part GF to EF, and I end up with this side with this angle, and this side congruent to this side, and this angle, and this side. So, SAS for number 5. Number 6. Here's what we're given, just what the diagram shows, and the overlapping triangles that we can prove would be U, V, Y, congruent to V, V, U, X. So that's what I can prove. How do I get there? Well, first let me write that. Triangle U, V, Y, Y, congruent to triangle V, U, X. Why is that? This is going to be angle side angle, because here's the side congruent to itself, so that was easy. But now let's look for the two angles that they give us. I've got this little angle here would be congruent to this little angle here. So now I've got one of my angles in the triangle congruent. But what else do I have? I've got the big angle. I've got this whole thing in here congruent to this whole thing in here. So now when I turn this around, I can talk about this angle congruent to this one. Whoa. So this is going to be angle side angle. Now, separate and redraw the indicated triangles and identify any common angles or sides. So we've got this guy, A, B, C, with B, C, D. BC is the common side. Now, on number 8, you can see this and this. And so this would be triangle, FG, FG, E, and H. So it's FG that's common to both. Number 9, I've got this one and this one. And they'll look like this. L, M, K, L, N is here, J is here. So here are the vertices of this triangle. The other triangle is right over here with its vertices. And so do I have any actual true common sides on this? No, they're not completely common. I need this part of this bigger side. So that's not common. What is common is angle L. So that's what we're looking for in number 9. Time for a proof. Let's make it a 2-column proof. And statements, reasons. We're always going to start with writing our givens, so let's do that. Ta-da, the magic of pausing a video. So what's our next step? Well, wait a minute. What's our plan here? I've got to prove that BYA is congruent to CXA. Oh, do you see what I see? Yeah, there are right angles in here, which probably means that I could use, oh, I don't know, HL or maybe LL. But maybe I won't get to use a side with another side. Maybe I'll have to go through some angles. So I can't predict, just because I see a right triangle doesn't mean that I'm going to automatically end up with the HL or the LL. So let's stay tuned. Let's see what we can figure out first. Well, I've got a right angle. That's kind of handy. But you know what? I didn't actually, they didn't give me, hey, you've got a right angle. What they gave me was, hey, you got some perpendicular stuff. So I actually have to say, I've got a right angle. So I'm going to do that. I'm going to say CXA and BYA equal 90 degrees. Or I could have said they are right angles, but it takes less room to write equals 90. So that's why I'm writing that. Now, why can I say that? Because perpendicular lines make right angles. I'm going to do RA for right angles. And that's sort of the definition of perpendicular lines, but this is sort of a definition idea that we can use here. Now then, what do I have? I've got this angle with that angle, and I can also stick in here all right angles are congruent, which is sort of an obvious thing, but I'm just going to write that in there because I needed to prove that I've got a pair of congruent angles. They happen to be right angles, but I'm going to use them. What else do I have? How about some reflexive property? What in here could you use, could you give me a statement for, and the reason is reflexive. Well, reflexive property is always blah blah is congruent to itself. So where in here do you have something congruent to itself? I need a piece of this triangle that is the exact same piece as in this triangle. Usually we've been doing congruent sides, haven't we? But this part of the triangle down here isn't actually part of the big triangle, this other triangle. Sure, we know that those are congruent, but they already gave us that. So what is it that's the exact same piece in this triangle as it is in this one? Hey, look at that. I overlapped my outline right there. It's angle A that is the same part in both of these triangles. So I'm actually going to do angle A congruent to itself. Reflexive property. Well, what do I have now? So far, I've got a set of angles here, and I've got A congruent to itself, which is like another set of angles. So I have two angles. Now, either I'm going to put a side in here, or I'm going to use a side here. Those are my only two options. So am I going to do angle, side, angle, or is it going to be angle, angle, side? Because right now, having proved two pairs of angles, the only thing I need is another side. Where's that side going to be, though? That's the question. Well, let's see here. Let's highlight this triangle again. So I got this guy in orange, and the things that I know that match up with the other triangle that I'm not outlining right now, I know that this angle goes with the other triangle. I know that this angle goes with the other triangle. And I know that this side, they gave me a little hatch mark, that side matches up to something in the other triangle. So what do I have? I have angle, side, angle for my congruence theorem. Was that what we were expecting when I saw a right angle in this triangle? Maybe not. Maybe if you see right angles, you're always going to try and make a HL or LL triangle congruence theorem. But in this case, it wasn't the case. So let me write my triangle congruence theorem. Because my reason is ASA, that means I must have made a statement about congruent triangles. So here it is, BYA congruent to triangle CXA. On to number 11. We have these two sides are congruent, FH, all the way from here to here, congruent to GE, from here to there, and we have this angle. Well, you know what? That kind of makes me think of a triangle like this, doesn't it? And another triangle over here, and I bet we could prove those are congruent. Once I have those congruent, I'm going to note that this side will be congruent to that side, and therefore I can look at this triangle that they actually want me to prove is congruent. Once I have this guy congruent to this guy, then I can say something about these being congruent, because I'll have this side congruent to itself, and I'll be able to use this angle from my original smaller sort of mid-sized triangle. So if you'll allow me to name this triangle the little one, then this triangle the medium-sized one, then these guys the large triangles. That's what I'll be referring to as we go through here. So let's make it a two-column proof. Statements and reasons. Of course, we're going to start by stating our givens. Now, let me clean this up and outline for you again where we're going to go with this. We already know that this side matches up to the other side over here, G to E. We also know that this angle is already congruent from my givens. So really, all it takes is one more side, and I've got side, angle, side for this mid-sized triangle. Haha. So can we say anything about FG congruent to, say FG? Yeah. Here we go. FG is congruent to FG. And it's okay if you wrote GF here. And by the way, let me also note that anytime you're using reflexive property, you are licensed to switch the order of these two. So it's okay to write FG congruent to FG, or FG congruent to GF. There's a little bit of theory here that that we're really measuring a distance, and distance doesn't have, you can't have negative distances. So if you're going forward or backward, you're still going to have the same odometer reading on your car, for example. So FG congruent to GF is fine. I'll accept that as reflexive property. Or you could have said FG congruent to FG. Again, both reflexive property. Use them any way you like. Continuing on. Now, let's look at this. We've got FH matches up to GE. We've got this angle, HFG, matching up with EGF. And we've got FG congruent to itself. So that means I've got one triangle here and the other one on this side. So now I can make a triangle congruence statement. Triangle, whoa, I can't even read these anymore. Triangle FGH is congruent to triangle. Now remember, we got to put these in the right order. So I got to start at G and go, I went from F to G to H for the first one, so I got to go from G to F to E for the second one. G, F, E. Why can I say that? Well, look at this. I've got a side, an angle, and a side, and when I note those on the diagram, a side, an angle, and a side for this triangle, then I've got SAS. But I'm not done. That's not what they wanted. They wanted GEH congruent to FHE. Well, guess what? The parts that make up those two triangles, G to E to H, that needs this side, GH. And look, I already know something about GH. GH should match up with FE. See, it's my second and third letters, and sure enough, that's what's happening. GH is congruent to FE. But I haven't proved that anywhere else. Guess what? It is time for CPCTC. Yay! Because these are corresponding parts from congruent triangles. So they're congruent. Great, so now I have this side congruent to this side. And let me look again at my little triangles. Until I said that these are congruent triangles in this step, I didn't know anything about this angle. Well, let's see here. This angle kind of appears, it would match up with this one. Does that help me at all? Well, since I know that I've got these two congruent angles, that doesn't really help me when I try to look at it in terms of my big triangle. That's just a part of another triangle. How can I do this? Well, let me see. What have I got so far for my big triangles? I've got this side congruent to this side from CPCTC. And, oh, look at this. EH. That's another part of my big triangle. Actually, it's a common side. So we're going to do some more reflexive property. EH congruent to HE. Look at that. I can mix it up. Reflexive. So now I've got this side, and oh, look at this. FH congruent to F8. Sorry, FH congruent to GE. That's actually one of my givens. So you mean I've got a side, and a side that matches up with another side, and side? Oh, yes. So I know these triangles are congruent by SSS. So let me make the congruent statement. And when I'm making the congruent statement for triangles, the reason must be one of my triangle congruence theorems. So if you say triangle blah blah is congruent to triangle blah blah blah, then you must put your reason as one of our many options. We've got SSS, SAS, ASA, AAS, and then if it's a right triangle, you have the option of HL and LL. So you must pick one of these every time you make a triangle congruence statement. Congruent triangles, one of these reasons. Here, we proved the three sides are congruent. So we've got SSS.